Welcome to the Explainer, everyone. Today we're taking lines of complex code and transforming them into your very own fully automated video production factory. I mean, just imagine having a complete, tireless team ready to understand, edit, transcribe, and assemble videos literally right at your command.
Okay, let's dive into this. What if an AI could direct, transcribe, and edit a video all on its own? We're talking about a multi-agent system that acts as an entire film crew, handling all the heavy lifting of video production. And honestly, the best part? We're going to see how this system lets you get this factory floor up and running without even needing any API keys to start.
So here's our blueprint for today. First, we'll meet your AI film crew. Second, mapping the master plan. Third, fixing the execution graph. Fourth, the video processing toolkit. And finally, generating the final cut.
All right, let's kick things off with Section 1. Meet your AI film crew and how we set up this lightweight runtime environment.
Stepping onto this digital factory floor, what's really interesting here is just the sheer flexibility of the setup. At its core, VideoAgent uses a multi-provider LLM wrapper. So that means it smoothly supports the major players, OpenAI, DeepSeek, Anthropic, Gemini, you name it. But let's say you don't have an API key handy. The system doesn't just crash. It actually has a built-in deterministic execution fallback, meaning you can run it completely locally or write in a Colab notebook without a hitch. It's a super robust environment that basically removes all the usual barriers to entry.
Moving right along to Section 2, mapping the master plan, or how we translate natural language into mechanical blueprints. So we're moving further down the assembly line into the planning phase. This is where your simple requests are broken down into actionable steps. And to really make sense of these highly technical workflows, I think it helps to personify our specialized workers as a real film crew. First up, we have the intent purser. Think of them as the director, analyzing your request and calling the shots. Then there's the tool router, acting as the equipment manager, figuring out exactly what capabilities are needed from the library. And finally, the graph planner steps in as the script supervisor. They make sure the sequence of events actually makes sense before anyone yells action.
Let's look at how this builds chronologically. When you throw a prompt at it, the director, our intent purser, first breaks down your natural language instruction to figure out what capabilities we need, like, say, transcription or summarization. Next, the equipment manager routes those necessary tools from the registry. And then finally, the script supervisor takes those tools and constructs the initial agent graph plan. It's this really seamless handoff from a human idea to a structured robotic blueprint.
Which brings us to Section 3, fixing the execution graph, catching mistakes before production. Now, think of this next step as a meticulous factory manager catching any blueprint errors right before they're sent off to the heavy machinery. You might see a term like textual gradient graph optimization and think, wow, that sounds incredibly dense. But let's de-jargon this a bit. Simply put, it's just the process of filling in the missing steps in our master plan. So if the AI realizes it needs an audio track to make a beat-synced video, but oops, it forgot to include an audio extraction step, this optimizer automatically repairs the graph by inserting that missing producer agent. It essentially guarantees that the plan is actually executable. To pull this off, the system structurally analyzes the graph across a few key dimensions. It verifies the topological order, which is just a fancy way of saying it guarantees step A securely and logically happens before step B. It also analyzes connected components, checks for any missing input data, and confirms that your original intent is totally covered by the current plan. And the system handles all this optimization mathematically. You know, while a human might just eyeball a script, the AI uses strict quality control metrics. These are represented by those slightly intimidating Greek letters tau, kappa, and chi. Ultimately, they just measure whether the current graph is structurally and semantically complete. Think of them as the strict mathematical bouncers that absolutely must be satisfied before any actual video processing begins. Okay, now we reach Section 4, the video processing toolkit, heavy machinery for multimodal tasks.
So our optimized, fully repaired plan is finally handed over to the heavy machinery for the actual execution phase. This is where we see exactly which tool handles the different types of labor required for a complex video edit. FFmpeg acts as the sheer visual and mechanical muscle. We're talking extracting audio, trimming clips, detecting scenes. Then Whisper handles the auditory labor, transcribing speech to get the timing just right. Meanwhile, clip-style models generate cross-modal embeddings. They basically act as the brain that understands how the text and the visuals actually relate to each other. But here's the kicker. All these heavy machinery tools don't just work in isolation. They feed their outputs into what's called a cross-modal index. You can think of this as a shared blackboard for the AI agents. This is where captions are perfectly aligned to video frames, keyframes are synced up, transcript segments are matched, and cross-modal data is embedded. It creates this beautifully unified workspace where text, image, and sound are completely synchronized and ready for the agents to use.
And finally, Section 5, generating the final cut, assembling the edited artifacts.
All right, this is the last stage of our automated factory tour. This is where all those meticulously indexed raw materials finally become a polished product. Let's look at a real-world example. Say a user types in a raw instruction like, make a beat-synced highlight reel summarizing the video content. That simple natural language sentence is the starting point that kicks our high-level agents into gear. They take one look at that shared blackboard we just talked about and begin their highly coordinated retrieval and assembly process.
By pulling from that synchronized blackboard, the agents can generate an incredibly impressive array of final outputs. Depending on what you actually ask for, the system can produce text answers to specific questions about the video, generate concise written summaries, stitch together full news-style video overviews, or even output perfectly beat-synced MP4 files. It literally turns raw index data into actual usable media artifacts. How cool is that?
Let's break down the final sequential actions that result in that seamless video. First, the system converts the index into storyboard queries. Then, it retrieves the most relevant scenes by mathematically comparing them using cosine similarity. Third, it fires up FFmpeg to precisely trim those specific clips. And finally, it executes a beat-aware montage assembly, laying the clips down perfectly to the rhythm of the audio track. Boom! You've got a fully rendered video created entirely by AI agents coordinating with one another. It is truly a fascinating workflow to unpack, which brings us to a final thought for you to chew on. As these multi-agent systems evolve to fully automate complex creative workflows, what human skills will actually become the most valuable in the director's chair? Will it be our vision, our emotional intelligence, or just our taste? It's an exciting frontier to consider as we start working alongside agentic AI. Thanks for joining me for this explainer, and keep learning.